So this presentation is going to be about finding the mean of a frequency distribution. And I'm doing it because some problems came up when one of these appeared in the homework, really in connection with a whole different issue. But the root of it is we need to know how to find the mean when we don't have the raw data, when we just have a frequency table. Okay, so I'm going to look at the eruption times of the Old Faithful Geyser. So this is the data spreadsheet for the class. And let me just read through what it says up here at the top, because you can use this information when you're trying to figure out the mean of the distribution. So the duration in minutes, how long did each eruption last? The duration was recorded for each of 299 eruptions of the Old Faithful Geyser. And so the geologists, they just used a stopwatch to measure how long it took from when the steam started coming out of the ground until it stopped. And they did this for 299 different eruptions. And this table here, the bin column is the upper boundary of each class. Okay, so if you look down here, let's look at this one, the 1.6 bin, okay, has a frequency of 5 eruptions. So what this means is that there were 5 times out of those 299 eruptions, there were 5 of them where the eruption lasted somewhere between 1.4 minutes and 1.6 minutes. So we do not know exactly how long any of those eruptions lasted. It's just there were 5 of them in that class. The 1.6 minutes is the upper boundary of the class. Okay. And so we have all this data. There were 26 eruptions that lasted between 1.6 and 1.8 minutes and so forth. You come over here to the graph, and it's a frequency histogram. And you can see there were these 2 types of eruptions. It's a bimodal distribution. And the mean, the average eruption, it's where the weight is equal on both sides. If you imagine this graph to be made out of some heavy material, made out of metal, or a balance point. And you can see that's somewhere in here. It's around, I don't know, maybe more than 3.2 minutes, certainly less than 4, you know, somewhere in the middle 3 minutes range, you know, 3.2, 3.6 minutes, something like that would be the mean, the average eruption time. And we want to figure out how to calculate that from the data. If you had a raw data table, you know, you would just add up how long does each one of the eruptions last. You'd add up the X values for all of the eruptions. There were 299 of them, so you divide by 299. And that would give you the average, or the sample mean. Well, we don't have X values, we have ranges. So we had 5 eruptions that were somewhere between 1.4 and 1.6 minutes. So roughly how long did each of those eruptions last? See, the midpoint of that class, halfway between the boundaries, halfway between 1.4 and 1.6, that midpoint is called the class mark. And so for this class, whose upper boundary is 1.6, the class mark, the midpoint of that category, is 1.5. And all of these 5 different eruptions lasted close to 1.5 minutes. So we're going to add up 299 different eruptions, and here are 5 of them, each one about 1.5 minutes long. So you add those up, 1.5 plus 1.5 plus 1.5 plus 1.5 plus 1.5. You get 5 times 1.5. Well, that's 7.5 minutes. So that's the sum of your first 5 eruptions. You take the frequency times the class mark here. Taking the F times the X. You get 7.5 minutes. And then there were 26 eruptions lasting about 1.7 minutes. So you add all those up. You do 26 times 1.7, and you get 44.2. So now we've added up the first 31 eruptions, 5 lasting 1.5 minutes, and 26 of them lasting 1.7 minutes each. And so 7.5 plus 44.2, whatever you get, that's the total time for the first 31 eruptions. And you add up all these numbers, all these, take the F times the X, and add all those up to get the sum of all the eruption times. Okay, so let me write this in symbols. So our sample mean one over the sample size times the sum over all the individuals in the sample. You're summing their X values. So that's 1 over 299 times x1 plus x2 all the way out to the 199th eruption. Okay. So x1 plus x2 plus the first 5 of them. There were 5 eruptions that lasted just about 1.5 minutes. See, so we had 5 times 1.5. And then we had 26 eruptions that lasted about 1.7 minutes. All the way down to the bottom here, where we had 3 eruptions that lasted 4.9 minutes. So those frequencies, the 5 plus the 26 and so forth, plus the 3, the frequencies all add up to 299. So in symbols, we're taking all the frequencies times the class mark. First frequency times the first class mark, second frequency times the second class mark, up to however many classes there are. Okay. So, how much is that? So you come over here to the spreadsheet. And we want to add up. Well, here we have all the frequencies times the class marks. We want to just add all those up. So, I'm going to do, to get the mean, I'm going to do 1 divided by 299. Okay. And then I'm going to make the sum of all the FJs times XJs. So I get 3.34 minutes. And if we look over here at the graph, 3.3, okay, it's right there. It's in the middle, 3.34 minutes. So we can believe it. And you notice my X values are reported to the nearest tenth of a minute. So I put one more digit on my mean. See, you can control how many digits are displayed, but with your sample statistics, it's standard to just show 1 digit more than the original data had. So these were to the nearest tenth of a minute. So I put this to the nearest hundredth of a minute, and I always include my units of measurement. So that's how you get the sample mean. Spelled wrong. Okay. And then let me just point out where this is in the workbook also. So in the workbook back here in the chapter on probability, we talked about this because it's analogous to how you find the mean of a probability distribution. I'll review that in this video in just a few minutes, but the first one place where you would have seen that is let's say back here under discrete random variables. There's this table. It's on page 322 in the November 2020 edition of the workbook. If you watch this video in the spring of 2021, the page number may shift a little bit, but we're finding the sample mean of a frequency distribution. And so you've got the formula right here, and you've got the definitions of all the variables and symbols down below. And then why did this come up in the section on probability distributions when I'm talking about a sample mean? It was to make an analogy. And the details of that If we go over to Canvas, back in that section on the discrete random variables and the media lecture and reading on that, there's this PowerPoint and a Zoom recording going over the PowerPoint about probability distributions of discrete random variables. Now that's not the same topic. What I was doing just now was the sample mean of a frequency distribution. The two processes are very similar. And if you go through this PowerPoint and Zoom recording, I'll talk about both and show how they're similar. Okay, but for now, in this video, I'm just gonna point out that similarity, try to use slightly different words this time and see how that communicates. So, oh, and I just want to fill in the number here. That was that sum. Let me get that real quick. You don't need to see this. I'm just adding up all my FJ, XJs in Excel. So it was so when I added up all the FJs times the XJs, I got 997.7. And I'm going to divide that by 299 minutes, and I get the 3.34 minutes, like I showed you in Excel just a minute ago. Okay, so now it's on paper as well. But now I want to show you something here. Let's look at this piece right here. You see, the way I did the arithmetic, I added all this up and then divided by 299. But you can also distribute. You could multiply the 1 over 299 times each term in the sum. You see, I could have brought this inside. I could have done 5 over 299 times 1.5 plus 26 over 299. I could add them all up and then divide, or I can distribute and divide each one individually, or multiply by 1 over 299. So I'm going to do that here. Yeah. So you see all I've done is distributed the 1 over n inside. And so each one of these so I'm taking the frequency of each class, dividing by the total sample size. It's the relative frequency. See, that's saying 5 times out of 299. It's the relative frequency, or it's the fraction of the time when X, the eruption time, fell inside the class with class mark what was it, 1.5. So that first class that had any data in it, the 5 eruptions, lasted about 1.5 minutes. Anyway, what fraction of all the data fell in that class? It was 5 out of the 299 eruptions. That's what you call relative frequency. And what we had before was the probability. So the Fj over n is just like the probability. What fraction of the time did you get a result in that class? What's the difference? Fj is gotten by counting. You actually measured the eruptions. You went out and looked at it. So this is real data. The probabilities are based on some theoretical model. Like all these problems about drawing cards or rolling dice or whatever, you say, well, if I did it long enough, I think all different sides of the dice would come up equally likely, this kind of thing. So somebody might have a model for how the eruptions work. Okay. So if I was doing the mean of the distribution, or expected value, I'd do this. Expected value of x. Okay. So it is confusing because we have sample means, we have population means, we have distribution means, 3 different concepts. Okay. And it's also confusing because this E for expected value, it's not the E that's the margin of error, that's a different E. So that's also confusing. All right, well, so that's all for this topic.